It is my pleasure to introduce our next speaker, Chung from University of Queensland. Please take it away.
Thanks very much, Jason. So thank you all for coming. And today what I'm going to do is I'm going to share some opinions that I have about planning with you. And the first one that I want to share with you is that I think one of the greatest selling points of robotics is that it offers us embodied agents that can act and affect change on our physical world. So robots like this one that you see here, it can grasp and manipulate objects, it can move its sensor to collect useful information. We have robots that can transport objects, we have robots that can transport people. But my first opinion that I'm going to share with you is that I don't think we've really explored all the ways that we can use their embodiment. And I think this might stem from our traditional approach to motion planning, which has really been to try and minimize the amount of contact that our robots make with the world. So if we're talking about navigation tasks, we want the robot to navigate collision-free. We don't want them to run into our walls or our furniture. If we're talking about grasping and manipulation, we really only want our robot to touch the object that it's trying to pick and nothing else. So as a result, I don't think we've really spent a lot of time thinking about how we can exploit physical interaction as a modality for perception, as a modality for information gathering, and for problem solving. And so my team and I, we're looking into ways that we can explicitly bring touch and physical interaction into the way that we do our planning and decision making for our robots. And what I hope to do by the end of this talk is to convince you that we should let our robots touch more things, and that you should also work in this area to help us solve some of the many problems that still exist in this domain. So what kinds of physical interactions do our robots do well right now? And I'd argue that they're pretty good at grasping at the moment. We really know very well how to get a geometric representation from 3D cameras, for example, which we can then use to plan grasp actions. We also know how to make the sensing part of this task more efficient through methods like active perception, where we only need to look at parts of the scene that matter to solving our task. So if we want to grasp a particular object, we don't need a perfect reconstruction of the full scene. We really only need to be looking at certain parts of the environment. We're also seeing robots conducting more complex force-based interactions over time, and Hannah showed some really excellent examples in her presentation as well. And a lot of these tasks begin by observing the scene, deciding on a point of contact, and then executing that particular trajectory that you've planned. And the basic paradigm that you see across all of these examples is that the robot is meant to look first, plan, and then execute that contact and hopefully solve the task. And if you don't solve the task, then you repeat those three actions. And so there's some general limitations here. And the first one, I think, is that we don't properly close the loop. So we don't consider how that contact, how that interaction can be used, first of all, to support perception. And we also don't typically consider interactions beyond the robot and that one object that it's touching. And I want to give you 3 examples where I think performing decision-making in this way really prevents us from finding good solutions. So the first one that I want to show you is work by my student, Tom Pitcher, and it's in cases where visual perception alone is not enough to solve a problem. So in this scene here, the robot's given the task of finding and retrieving a purple block. But all it can see is this cup here. And if I were to ask anybody in this room, I imagine you would all say it's probably under the cup, right? If the block is definitely in the scene and all you can see is this cup, then it's probably under the cup. The problem is that there's no way that you can look. There's no place that you can put the camera alone that's going to reveal that information to you. So is it game over? Well, no, we've just established that our robots are pretty good at grasping. So in this sense, we should get our robots to physically interact with the environment, pick up the cup and actually have a look at what's underneath it. And so physical interaction in this case can more efficiently reveal hidden parts of the scene. So it doesn't just have to be in cases where the object is completely enveloped by something else, but it can help us to improve and make our perception more efficient. And it also can make solving the task actually possible. So it can make objects, in this case, more accessible. So the question still remains, though, how do we actually incorporate this option of physical interaction into our planning? So in this scene here, let's say the robot's trying to search for and retrieve a rubber duck, and from its first view of the scene, it can't actually see a rubber duck anywhere in here. Now, it might have some information about how large this object is that it's looking for, and from our understanding of perception and 3D geometry, we can get a reconstruction and start to infer where this object might be hiding. Now, we've got two options available, two types of actions that our robot can take. Either it can move its camera to view new parts of the scene and reveal parts of the scene that are currently hidden, or it can choose to grasp and remove objects, move them out of the way so that it can reveal parts of the scene that way. Now, in order to plan between these two actions, and in fact, in order to plan for any action, you need two pieces of information. The first one is that you need to know the conditions under which you can successfully execute that action. And people who work in symbolic planning, you would know this as your preconditions. The second thing that you need to know is what is the effect of your action. So if you successfully execute it, what's the outcome in respect to the task, your desired goal? So once you have these two pieces of information, once you've defined these two, you can really plug your action into any decision-making pipeline. And indeed, what Tom does in this case is that we formulate it as a Markov decision process, and we solve it using reinforcement learning. And so it's no surprise that when you explicitly consider targeted use of physical interaction as an additional modality to solve a task, like in this case, we want to retrieve that green block that's in the foreground but is blocked from the view of the robot, you end up being able to solve that task a lot faster if you use physical interaction as one of the modalities that will allow you to solve this problem. But in this example here, what I've shown you, we're still only looking at one robot interacting with one object at a time. So now let's have a look at our second example, tasks where multiple contacts are either inevitable or that they can be used to really speed up how we achieve our goal. So this is my cup drawer at home. It's a bit of a mess. And I'm regularly faced with this problem of needing to put this cup into this drawer. Maybe not exactly this cup, but I need to put a cup back into this drawer. So I like to think of this as the peg and hole problem, but in expert mode. I call it expert mode because there's not a perfect cup-shaped hole in this drawer. But I know that this cup fits in the drawer because it fit in the drawer yesterday, so it's got to fit in the drawer today as well. So if we were to only allow a robot to interact with one object at a time and only be able to reason about one-on-one interactions, then this could be a very slow process, right? You could have to move one cup a little bit further away, move another cup further away to finally alleviate enough space that you can actually insert this cup back into the drawer. So that's option number one. The second option is the one that I think most of us would use, which is you grab the cup that you're trying to put in there and you push all the other objects out of the way until you can actually fit it in there. And so what we'd like our robots to be able to do really is to exploit these kinds of chains of interactions. So not just considering these one-on-one interactions, but to think about, well, if the robot is holding an object, can it push on some part of the scene? Will that have some effect on some other part of the scene? And being able to reason about all those chains of interactions going down in terms of how that is going to be able to support solving the task that it has at hand. Now, as always, we still need those two factors. We need to understand the preconditions, so when can we actually execute this action, and we need to know the effects of executing this action in space. And so now when we're looking at these kinds of interactions, they're a lot more complex than when we're talking about peg and hole expert mode. And so this example looks like we've solved the task, and this is work by Haoyuan Liu, my PhD student. But indeed, behind the hood, it's indeed a human teleoperation. So she's there controlling the robot and demonstrating this task to it. So using human demonstrations can be a tool for us to try and model what these preconditions and effects are so that we can incorporate these types of actions into our planning pipelines. And our initial tests on these have shown that these kind of modern models of diffusion policy and so on, 3D diffusion policy, we can use these tools with fairly limited human demonstrations to start to mimic some of these actions. And so with roughly tens of demonstrations, we can already start to overfit. And that's kind of a good thing because if you can't overfit, then you really have no hope of learning anything. But the problem is that human demonstrations are expensive. And if you want your robot to be able to use this type of action in general, you really don't have the bandwidth to be collecting this kind of human data. So what can we do? How can we actually generalize beyond the kinds of data sizes that we need in order to solve this? And I think here it's useful to leverage all of the tools that we have available to us. So whether we can use these kinds of simulators, these very powerful simulators that we have, to help us provide enough experience to the models that we're trying to train to understand the effects of these types of multi-contact interactions. We're not necessarily trying to train it on a specific task. We can try and refine on it after the fact, but we need to give our robots and our planners some way of understanding how physical contact works in the real world. Now, I think it's pretty important the fact that the planning session happened after the haptics session, and talking about the topic of planning to see and touch. And so people who have been around since the previous session would probably be busting out of their seat to tell me that if I'm going to have the word touch in my title, then I should probably acknowledge the need to also incorporate modalities such as force and torque sensing as well. So the third example that I want to give you is what happens when the tasks that we want our robots to do are not just about contacts which are either binary or incidental, but the contact is really the task altogether. So in this example here, I like to describe it as the piano mover's persistence problem. So in planning, we have the piano mover's problem. How do you actually move these kinds of bulky items through this space? And I've had to move apartments 3 times in the last 3 years, so I've been thinking about this a lot myself. And for me, I mean, I know how I would like to move these bulky items through space, but what I really need help with, and what I really like a robot to be able to do to support me in these kinds of object load transportation tasks, is to be able to follow in a compliant way. And at the same time, I wanted to maintain contact. I don't want to have to be pulling it. And I also don't want to have to worry about that robot running into the walls as I'm maneuvering around doorways and so on. So now we have this kind of multi-objective task. Our interaction is no longer just binary contact. Planning needs to operate now at a much faster reactive feedback cycle. And so my student Luigi is looking exactly at this problem here. So you see our kind of gazebo environment on the left-hand side, which just shows you where the obstacles are. And on the right-hand side, you can see the whole robot, the full body of the robot being visualized. And here the robot is experiencing a force at its end effector, and its goal is to minimize that force, so minimize the pulling that it's acting on the user, but at the same time navigating through the space so it doesn't run into any of the obstacles around it. And so in this case, we use a lot of tools such as model predictive path integral control, and rolling forward all the possible actions that can happen into the future, and then reasoning about which are the most optimal set of trajectories to take. So I've given you 3 examples of places where I think physical interaction can be extremely useful for our robots, and that we should try and increase the ability of our robots to do this. So first of all, physical interaction is a modality for perception, being able to exploit chains of interactions to solve problems, and planning and control for continuous interactions. So I want to leave it here. I want to thank, of course, all of my students, my team, and our collaborators. And as a very, very quick plug, the University of Queensland is currently hiring. We have multiple faculty positions open, so please take a look at the QR code. Happy to answer any questions about that as well. But thank you very much, and I'm happy to take any questions.
All right, thanks very much. So it's time for a few questions.
Yeah, hi. I was wondering, your problem with the cups seems to me like a really good problem for reinforcement learning. And you've solved the problem of fitting the cup. Have you looked at, let's say, optimal fitting, or how many maximum cups that I can fit, those sort of problems? Have you
Yeah, actually, it's a very challenging problem to solve for optimality, because you think it's a geometric problem, right? You should be able to solve for this. But it branches very, very quickly in terms of what you can do. So potentially reinforcement learning is the right way to go, because often the goal isn't to pack optimally, it's just to get everything in there at all. So again, I think in some of the previous keynote sessions, we've also looked at user preferences as being part of that optimality question. But I think in this case, what I wanted to emphasize was that when you're looking at contact and interaction and planning over those, these kinds of chains of interactions are really a blind spot, I think, in terms of how we understand and how we allow our robots to interact with the world.
Oh, hi. Sorry, I don't know if you covered this and I didn't understand it, but I was wondering if you consider if certain types of interactions are unsafe, or if certain objects can't be touched.
Yeah, again, very good point. The last piece of work that I showed you in terms of that shared load manipulation, safety is a huge part of what we are concerned with in the solution, right? We need robustness, we need to make sure our system is passive so that we're not injecting more energy into the system indefinitely. So the way that we solve for it there is that we have it as a critical part of our objective function that we're optimizing over, and we also use tools like energy tanks to guarantee passivity. For maybe what you were mentioning also is thinking about, if it's an egg, you don't want to be smashing that into the drawer, or if it's a cup that's particularly delicate, you don't want to be hitting that against other objects. That's a little bit more challenging. I think there's going to be you're going to need to have a way of being able to specify that either in the definition of your task to say this particular cup, this is the one that I don't want you to break, whereas these ones, they're made of plastic so you can do whatever you like with them. And so if there's a way to inject that knowledge into your system, then that becomes part of those preconditions. So when you can actually execute a particular kind of action.
Thank you.
One final question.
I guess another way to approach the planning problem is having like a LLM or something instead of training into a policy to reason over. So I guess what are the reasons we would want to have a policy basically do this exploration, which might be less interpretable, or maybe you couldn't reason over things like, I guess, safety, like previously mentioned?
Yeah, I think I saw in a previous talk as well that LLMs are still somewhat disembodied, right? They're based largely on text and camera images so far, and that really removes it from the physical world in some way, because we can talk about being gentle with eggs all we like, but until you touch one and physically manipulate one and crack one open, you don't have a good idea of how much force is too much force. And for this particular embodiment of a robot or that particular embodiment of a robot, these thresholds are all going to be a little bit different. So while I think LLMs are very powerful tools for reasoning at the kind of verbose level, I think we still need to have something that grounds them to the physical agent and the physical task.
Thank you.
Okay, thanks very much. Thanks.